you guys can all read. I won't read this title. Go for it.
Yeah, so this is an excellent moment to have this title because LLMs are there to save us from all manual work in the future. That's at least one of the promises, although I don't think it's quite that simple. So first I would like to say what I mean by avoiding manual work, and because this is very typical in and popular in natural language processing, that you want to do things avoiding manual work. My closest reference is tasks which have some kind of translation where you go from some source to some target, and then you have some machine learning that gives you the procedure from going to the source, the target. So is there any manual work? We'll see. Then the contrast to this is some rules, which are then supposed to have a lot of manual work behind them. So for machine learning there is some manual work, some small constant k. I don't know how small it is when you have companies investing billions of dollars on this, but that's at least the idea. And it may remain here because you are happy with the results. But if you are doing something really mission critical, like for instance translating documents for publication, then there is manual work for every instance of this translation, and you can't really escape going through everything, checking it and correcting things. And this means that there is another factor, c, which is then the manual work is a linear function on the output that you produce, so that the total cost for this is k plus c times n. And so there will be manual work, and this is of course acknowledged by companies that use machine translation, for instance, and then they use post-editing on the documents. So what about rules? I would say that at least in proper usage of this thing, so you don't do manual work on the target, but when you find that something is getting wrong, then you do manual work on the rules, and this will, again, with some assumptions maybe, and this square root is just an example of a sublinear function, that you are improving the rules so that you have to do less of these improvements as you go. So the constants here, the k and c, are way bigger than in the machine learning situation, but in the long run this will pay off.
So yes. This is square root derived from some Zipf's law distribution? Or?
Yeah, so something I would like to actually approximate it both mathematically and empirically in a better way.
Is the n?
Sorry?
Is the n now the number of rooms? Or
it's a number of output input items. Yeah.
And you're saying that little k is much less than big K.
Yeah.
It's not an amortized computation, right? So when, sure, from your point of view, if you use a pre-trained model, little k is tiny. But if you amortize over the whole cost of training that model by somebody else, that little k might be much larger.
Yeah, I'll come back to that actually. Yeah. Very good question. Also, all of these are very good questions. So then there is a third approach, which I'm going to present to some extent, is that you use machine learning not for the direct transfer from source to target, but in order to learn rules. And the advantage of this is that this gives you explainability. You can look at the rules, like you do in the rule-based thing, and then you get into something which is probably a bit better. So you have a smaller constant. You have a smaller constant for building the rules than you have when you manually build the rules, but you still have this sublinear cost in the long run. So what avoiding manual work means in natural language processing nowadays is always machine learning. there is a low initial cost, but and this is kind of okay in many applications, like I don't know, sentiment analysis or information extraction, as we saw in the previous talk. But then if you are in something, making something mission critical, like I think formalizing mathematics, then you are not happy with that kind of results. Rules also avoid manual work because you do one thing and then you get infinitely many things, or potentially infinitely many things. There's a high initial cost, but if you follow this discipline well, so you never need to correct the target results, but instead you correct the rules, and then you get improved performance along the time. In the best case, the rules can even be proven to be correct, which is not, I think I will not arrive there, but it's of course the best case. Another very, let's say, common sense way to avoid manual work is that you don't repeat work. If something has been done, so you don't do it again and again. And the key here is to reduce own and others' work. So you don't throw away knowledge that is 20 or 200 or even 2,000 years old. You have 2,000 years old knowledge in both mathematics and linguistics, which is still valid. Euclidean geometry and Greek and Sanskrit grammar, for instance. Yes?
I don't know if I can object, but like you have this counterexample in AlphaGo, AlphaZero, when it really came up with openings that people, the quote-unquote experts, considered to be dead. Yeah. And like the humans really learned from the machine how to play some of these.
Yeah, this can also happen, of course. Yeah. But then it just shows that the knowledge that we had before was not that good. Yeah. So, but okay, all of this is a bit kind of relative. But one should also, we are working on rules or software, so we should try and build things that last, so that others can then avoid manual work. Even if we do some manual work, we can take some honor in that we save work for others. Abstraction here is going a bit deeper, so one should make the rules more and more general. You have rules that produce rules that produce rules, and since we are in kind of a functional programming and mathematical context, so rules are formally or technically they will be functions that produce functions that produce functions. And then there is a meta-programming, which is something similar. So the use case I'm looking at is the InforMath project that I was talking about 3 weeks ago. Time flies. And what I'm going to show in the continuation is actually mostly work that I've been done while here. So there is a kind of an estimate of manual work that comes from that. So inspired by people, but also having the kind of possibility to sit down in the office and work undisturbed, but then from time to time getting inspiration and help from others. So this has been such a marvelous situation. So this is the InforMath picture that I showed. So we want to have this convergence between natural language and formal language for mathematics. And by natural language we mean many natural languages, and by formal language we also mean many formal languages. So we want to have some kind of an interlingual setup on both sides, but then I think it's a bit too much to assume the same interlingua for both sides. I talked about this last time, so you can see there. So the important thing is that I want to distinguish between the solid and dashed lines. So the solid lines are the rule-based components that are meant to be verifiable, even provable in some cases. and the dashed lines are produce results that need to be checked and corrected. And that's what comes from machine learning, and that's also what comes from human input or human interaction. That's why we need proof checkers in the first place, that we don't trust humans, right? The focus in this talk is on that part where we interpret natural languages and convert those to this abstract syntax for informal mathematics, and we use machine learning, metaprogramming, and grammatical resources in this task. So the goal is to build a lexicon of mathematical terms with their grammatical structure and inflection, so that we can use these terms in different contexts in a text, and then find translation equivalents in the mathematical domain between the terms. This is used in a syntax that at the moment consists of statements and definitions. I haven't really looked at proofs yet. So how we avoid manual work? In the lexicon, so we use, we get grammatical structure and inflection from two sources. One is the GF Resource Grammar Library. I will repeat a few words about that shortly. And the other one is a machine learning technique, namely universal dependency parsing, which is a general purpose machine learned parser for many languages. For translation equivalence, we rely on Wikidata labels. So we are not trying to correct them, and they also seem to be quite a good quality when we look at the mathematical part compared to some other Wikidata that I've been working on. For the syntax, we have Fortel, which many of us know here as the starting point, but we're not restricted to Fortel. We can extend it, and I will say more about it. And then we use the GF Resource Grammar implementation to re-implement Fortel in a way that can be then made multilingual, and where you can nicely insert these mathematical terms with their structure that we find in the first part. And then we will use functors that have shared grammar modules for many languages, so we will also show that. So what is GF, Grammatical Framework? It's very briefly, it's logical framework plus grammar. And it started actually with ALF, another logical framework. So who of you know ALF? Yeah, that's very nice. So it's the ALF from 1992. And GF is actually very similar to ALF. So you have three forms of judgment, basically. So there is categories, functions, and definitions, and I have marked as in gray because we will not use that part so much. I also marked the gamma in the category in gray because it is for defining dependent categories, and this we are not using here now because we'll rely on the dependent types on the side of the formal language. So that's like LF, very much like ALF. I've also understood that it's quite a lot like Deducti, so very simple framework instead of definitions. So these are pattern equations, actually, the definitions, and in Deducti they are rewrite rules, which are kind of a bit more general. So concrete syntax, for each cut we have a lin cut, or linearization type, and we have a linearization function that produces something. Then we have two other forms of judgment I will introduce shortly. So the idealist concrete syntax is actually a kind of a semantics, compositional semantics, or homomorphism from the abstract syntax to some space of strings and other things that I will show. So here's a simplest thing where the linearization type is a string, and this is what corresponds to context-free grammars. So we have a category prop and a category term, and a function even, which takes a, no, it should be the other way, right? A term into prop, sorry. This is, I hope you understand. And even applied to x is defined as x concatenated with is even. So rather simple, but reflecting a moment, you notice that you would also need all numbers that are divisible by 8 are even, for instance. So you need both is even and are even. So how we do this? We don't want to extend the abstract syntax because it's the same function even, but instead we, in the concrete syntax for English, we generalize a linearization type. So we say that the term is a string together with a grammatical number, and now we have the param definition, so it's either singular or plural, and then even is the string of x and with the copula, the verb be, where we select the number of the subject and then even, okay? Don't change the abstract syntax, but we get both is even and are even, and also guaranteed to be grammatically in agreement with the subject. In French, we do something similar, but still with the same abstract syntax, saying that we also need gender and number and mood, indicative and subjunctive. The concrete syntax changes, but the abstract syntax remains the same. So in this way, we define these reversible mappings that are used, look like linearization rules from the abstract syntax to the concrete syntax or the strings, and then parsing is derived from this by a rather advanced algorithm, which at the moment, the one that we are using, it's written by Krasimir Angelov. And the power of this comes from the multilingual grammars, where you have one abstract syntax paired with several concrete syntaxes. And some of these concrete syntaxes could actually be formal languages like Lean. So we saw last week, I think, Shashank Pathak showed this kind of translation between English, Fortel, and Lean. And this gives us the picture that I just wanted to show. We also had it for a long time, but I saw something similar for deductive, I think yesterday. So this is the interlingual translation model, which gives us a linear scale up to a quadratic number of translation functions. What we have in the resource grammar, so we have these functions for building lexicon. We call it smart paradigms. So for instance, if you can, a very typical thing that you need to do for English is that you form a plural of a noun, so you don't just add an s, but you have a kind of a pattern matching over the noun. And here we are covering some of the most common cases, and sometimes it doesn't help, but we have to give both the singular and plural. So this is an overloaded function. So you see the examples here. And then in addition, we have a syntax, and the paradigms, the smart paradigms are different for different languages, because we saw French, for instance, has many more inflections than English for adjectives. German has even more, and they have their own smart paradigms in the library. But the syntax API is to a large extent common. So, for instance, here is a set of overloaded function for building clauses by adding a subject NP to an adjective or a verb or many other things. And this is, as we will see, also usable as a functor interface, so that it enables us to write a grammar for many languages at the same time. not only the abstract syntax, but also the concrete syntax. So here is just an example of how you, for this little grammar, which is, we still have the same typo in the type of even. So in the functor, you can say that the linearization type of propositions is clauses, and for terms is noun phrases, and then for even, you just apply the make CL for some adjective even, which is a parameter in the functor that you then define in different ways in different languages. And here is the coverage of the resource grammar. So there have been many informal projects using formal, informal translation projects using GF, and I think I will just not go through them, but I will put a link to the slides on the spreadsheet. So now let's go to the new things, lexicon extraction from Wikidata. So we use Wikidata, and from Frederick and from Lucy, I got a list of, in total, 5,381 terms that are for mathematical concepts, extracted by different queries of Wikidata. And then we have the GF Research Grammar Library, and then we have the UD parsing. More accurately, we are using the UD pipe from Prague, which supports maybe 100 languages. Mathematical concepts, so they can be single words or they can be multi-words.
Excuse me?
Sorry?
The original list is in English or?
So,
what is
in
the
Wikidata.
reference?
Sorry, in...
The original list of terms here
Yeah.
we're talking about is English terms.
No, they are Wikidata identifiers, and they have labels in different languages.
Okay, and this list was done by hand.
Someone was, I mean, the
No,
community
because
has...
the articles
Yes.
in Wikipedia change a lot about the different languages.
But Wikidata is different,
Yeah,
right?
Wikidata
is
is
a
a-
structured version of
Yeah.
Okay,
Wikidata.
you take the structured version. Okay.
Yeah,
What is
Wikidata is a database
Yeah, that's fine.
underlying, but it's not yet used in all of the Wikipedia. So it's an emerging thing, but it already has...
I mean, the labels are defined from the Wikipedia articles. The initial
Not all.
set of QIDs
Not all. All the ones that are in
Yeah, no, but
Wikipedia are
they were
Wikidata, but there's
generated
new ones.
from the links. No,
Yeah,
I
but-
mean, they are all the data which is initially there comes from Wikipedia. So for each Wikipedia article, there's at least one Wikidata item. So from this direction, it's complete. So all Wikipedia articles have corresponding Wikidata items.
But there is also, so you can add things manually to Wikidata. So it's, I don't care about where all of these come from, but just that they are about mathematics. So it's,
Yeah, but that means that for every Wikipedia article
Yes.
about a mathematical topic, there is at least one Wikidata item.
yeah, so
It's very
hopefully, yes.
automatic,
Yes. So, so these are in general multi-word concepts. Of course, in German there are less multi-words than in English because you can build compound words. And then, depending on the grammatical structure, for instance, you inflect different parts of the term, and it's not always just S, but it could be ES or something like that. And then this you can know if you know what the head word of this is, and that's the first step in the grammatical analysis. So last time I showed something which was version 1, where we have a heuristic rules for analyzing these multi-words and then just applying smart paradigms on their parts. And this was a very rough and quick way of doing it, but and which was a very small K for the initial work. But now we want to use the knowledge better than at the time. So that's what I've been doing while here. So we are building a grammar with, at the moment, 21 extraction functions, which correspond to different forms of the wiki data terms that we have observed in the labels. And then we use morphological dictionaries that are given in the resource grammar library, varying sizes for different languages, so that we don't need to heuristically guess the inflections, but that we can actually find them for many words already there. Although in mathematics there are lots of words that you can't find in normal dictionaries, so that's the makes a difference. So the main thing here is a workflow for metaprogramming. So it's a Python program, sorry for that, but Python is very good at doing this kind of things. But it also uses GF parsing. So I want to show this in a live demo now. So can you see this well? I will make it much bigger. So I will do it for German because we're in Germany. So and there are maybe many Germans here. So, I have done this for 7 languages, and in the workshop we could actually try and add some more languages. The first step is to extract Wikidata for that language and we find that of these terms, so there are about 2,400 that have no German labels, so we just ignore them now for the moment. Then we do step 2. We parse with UD pipe, so this will take some time because parsing always takes some time, but it's not too bad. So in the meantime, we can look at the UD parses for German. So I have converted them into nice trees. So we use this information. There are similar things for French. Step 3 is use the UD byte parse to clean up corpus and add to lexicon. So this is, there's for instance one cleanup that is needed is that very arbitrarily some Wikidata labels are starting with a big capital, and that's not something that you, it's just, in German this is a bit less often because nouns start with capitals, but in English and French this was a real problem until realized this. So we had to fix the case of 200 terms, and then we get new words suggested with a bit better information than just the smart paradigms, because the UD parse gives us some morphological information as well. So we get 2,691 new words. Then we built an extension of the lexicon. And we had 44,000 in the original morphological lexicon, and here we got this number of new ones, and now we have a new GF file. And now comes the thing that can take a lot of time, but for German it's for some reason quite simple. So we have to first compile the new grammar. There are also some probabilities used in the parsing. Not go further into this. So it didn't take too much time. So we could parse actually vast majority of those German terms with the GF extraction grammar that we had. So now we have a nice grammatical structure and morphology for each of them. And then the final step here is to then extract the math terms.
You skipped step 6.
Yeah, so step 6 is when you are putting the first language here. So this is, so
Fine.
yeah, thanks. So now we have the lexicon, and we can also test it. So it generates some random terms, and then if we are happy with those, and we can do some more random text tests. You see, you need many inflection forms because they have adjectives, and you have to deal with both mixed and weak and strong declensions of the noun phrases. So this is the way it is. So now let's go to the syntax. So it's based on Fortel, and we have Paskevich, Andrei Paskevich original article, and then we extend it with wiki-based lexicon in particular, but also LaTeX formulas that were not in the original one. So the starting point was Shashank's work last week, and then we have functor over GFRGL. So first of all, the definition is in context-free grammar, so we made it into a more abstract GF grammar, which also doesn't take these numbers as free variants, but it selects them by agreement. And then, so we had some code, and then we have a functor, and then sometimes we need to make exceptions to the functor or set some parameters. So in particular, for the core Fortel, we need these structural words. And a little secret also using machine learning in a way is that if there is a language that I didn't quite know, so I tried Google Translate, and then I copied the strings to here. So yeah. So and now I want to show the final demo. I hope we have a bit time for this. So I'm just parsing now the original. You maybe remember, if you saw Shashank's talk, that he had simplified the statements from some textbook in order to convert them to lean. So what we wanted to do here is to actually parse the original examples, and this is what we are. It's a bit more than a half, and then I stopped. I think so. There was some little work to do on that, but then I can also use this for translation. So if I translate this to German, and I just show all of the results that we got for the German translation, and since there are also Portuguese speakers here, so let's look at the. I'm sorry. Oh, okay. And I have Portuguese. Oh yeah, I don't have it here, that's true. I have French. I have Portuguese in the other branch. So we have some French speakers as well. Yeah. So, but then the other branch I have, so here I didn't have the big Wikidata functions, but here I have, and I show some funny examples of that are random fillings of the "there exists no" statement. Yeah. And so on. So now I think I should be done. Just the conclusion of what we have done and what it has cost. So 30 to 60 minutes per language, adding here, relying on the first language and the workflow that take a big K of the 2 weeks work. And then if you don't have a resource grammar, so then you have to spend a few months doing that. So there are many more things to do, and for instance, I think some more uses of machine learning and even large language models, but if you have some suggestions, so they would be very interesting. And I welcome everyone to the well, there were 12 people who were interested in the working group, but we can work on this a little bit more in depth and try and see, build some more things. Thank you very much.